I understand that many people are not, do not wake up in the morning just wishing to do more math. And so there's a little bit of a challenge as to how to get across a message of what it is that gets me up in the morning without scaring people off before the reception, because that'd be terribly rude. So I'm warning you that there are some pictures of mathematics in this little presentation, but you don't actually have to know any math to look at the pictures. All right, so okay, with that, this collection of computer algebra systems and things that were mentioned earlier happened in a number of different places, at the University of Waterloo, at the IBM T.J. Watson Research Center, at INRIA in France, and most recently here at Western. And all of these involve computers and mathematics and some other things, but it's about the intersection of computers working with mathematics and mathematicians working with computers. So what is computing? We've been computing for a long time. There's that abacus is computing something, or could be used to compute something, just like that 1960s era computer could be used to compute something. Once we wanted to compute more things, we had to get electronic help. Now, what are the kinds of things we want to compute? And what is an answer? So here's an example of a problem of the kind that caused many people nightmares. All right, so one day somebody's going to the horse races and they want to count the horses and the people, but for some reason, related mostly to testing, they counted the heads and the legs rather than the horses and the people. We have to figure out how many horses and people there were. And we have to invoke certain knowledge of the real world. For example, that someone is a being is either a horse or a person. You can't be both. That horses have 4 legs, people have 2 legs, and so on. So we can set up a set of equations that if we add the number of horses and the number of people together, we get the number of heads, and likewise an equation for the legs. And so there we see we've got 74 horses and humans together and 196 legs, and if we can solve that system of equations and figure out how many horses and people there were. We're not going to get into how we solve that, but if you attend some courses here in the first year, you can learn how to solve this and figure out how many horses and people there were. All right, so the whole point is that we've come up with an answer. An answer is a number, all right, in this setting here. But computer algebra is all about saying numbers aren't good enough. If you remember the book from which this number came, the whole point was this is a useless answer. That you actually have to know more about the context and what the question was being asked and what the other possible answers were in order to be able to interpret the answer. So a fellow by the name of Dick Hamming, who is one of the pioneers at AT&T Bell Labs, the place from where Unix comes and from which Linux and all of this heritage comes, his main point, in the dedication to his textbook, Introduction to Applied Numerical Analysis, he claimed that the purpose of computing is insight, not numbers. This fellow is known for a lot of things, in particular his fashion sense. All right, so here's a better answer. This shows us that, well, yes, it's 42 at some point, round about when x is about 1/2. Yes, the answer is 42. But if you change the input a little, this shows you how it changes. So we've got a picture of it. Now, a picture is not particularly useful if you want to do things with the answer. So a more useful answer might be to have some polynomial function. And here we see that this green line is the polynomial that goes through the data points that we had. Okay, or approximately so. And so we can use this to control exactly how fast your automatic braking system sort of makes the brakes come on when you press hard on the brake. You can use a function like this. But it turns out that wasn't the right answer. The polynomial is that red thing, but the right answer was this other function here that went through all of the points. And we see that it's of a very different nature. The correct answer wiggles up and down. Whereas the number that went, the polynomial that went through all the points, well, it did go have all the right values on certain points. Actually, when you go beyond the range at which you actually had data, it turns out to be desperately wrong. And I wouldn't want to fly in the airplane that's being controlled by the red polynomial if the green stuff was the truth. All right, so that's what computer algebra is all about. It's in getting some exact, meaningful answers instead of just working with numbers. All right, so instead of saying 6.28318 blah, 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 it's more meaningful to say that that's 2 pi. All right, so if I said that's 2 pi, you can remember it, you can work with it. And in fact, that number up there is actually wrong. It's not actually exactly equal to 2 pi because pi has more digits. It goes on forever. So the whole point about computer algebra is to have the computer figure out what the formula should be rather than using formulas that people give it. Or maybe taking formulas that people give it and then going and figuring out other formulas that are the answers. And to do that, we need algorithms and software. So the whole point is that we're going to start computing with symbols and continue computing with symbols so we can get exact results that are hopefully insightful. So here's an example of a computer algebra formulation for the horse racing problem. We're going to have h heads and l legs instead of some number of heads and legs. And then we'll write down our equations with h and l. And then we'll get the answer in terms of h and l. And we can tell by looking at this what happens if you had more heads. How would that affect the number of horses? You can tell rather exactly what's going on. All right, so here's an example coming from computer algebra software, which I was involved in writing together with many colleagues over several decades around the world. So here's a maple session. We're starting off by multiplying some numbers. Now we can see they can be as long as you like, and they give you long answers. And they could go on for many screens, but I'm trying to fit it onto one thing here. All right, so here's another example. Here's a picture of some mathematics. This is called a polynomial. You can type that in, and it will give it back to you. But then you can do things with it. For example, if you remember your high school, you might want to expand out that polynomial, multiply it out. And so there you go. There's that polynomial expanded out. Or we can take some sum of things, and then we can ask to factorize that polynomial going in the other direction. So what Maple does, and what other computer algebra systems do, is they take these kinds of mathematical formulae, and they allow you to work with them in much the same way that you'd work with sentences and words in a word processor. Think of this as being a math processor. All right? So you can also do all kinds of calculus and things here. So the pointer in this doesn't work for some reason. But there I'm asking to compute some function from calculus. I'm integrating some function, and it gives me some things we could go on and talk about. But you have to be careful what you ask for. Okay, so here you see that little wee black thing that looks like it's about 1/5 of the width of the screen and impossible to read, just the very top. That gives this answer, which you only see the first page of it here. All right, so you have to be careful what you ask for when you're working with computer algebra. Now I'm going to that was a computer algebra software. I'm going to talk about computer algebra algorithms for a second. And again, this is a very tutorial example. This isn't the kind of stuff we do our research on, but it's to give an example of where things go. All right, so here are 2 polynomials, p and q. And you learn to multiply those. Everybody in this room has learned to multiply together polynomials. And some people still have bad dreams about it. Okay? And this is the school method for multiplying together polynomials. You see? You write one above the other, and you multiply. I really wish this pointer worked. You multiply the entire top polynomial by 7. And then you get the first polynomial under the line. And then you multiply the whole polynomial by x. And you get that second polynomial under the line. And you do that for each of the terms in the bottom polynomial, and then you add them all together. All right, so now if there are d terms in each of those polynomials, this takes about d squared work. Okay, that's how much work you have to do. Okay, now, that's a bit technical. It's a bit edgy. I was worried about that. Okay, well there's another way to do it, which I'm not going to go into the details, except to say that you don't have to do it in the ordinary school way. You can use a more complicated way to multiply them by evaluating the polynomials at points, feeding in numbers, getting numbers out, doing some stuff with. And you might say, so? All right, so the point is that the classical algorithm, the school algorithm, is this red curve on the left going up. And the complicated, fancy one that was too complicated to explain in 30 seconds is the green curve. It's always more expensive, way more expensive, for problems of the size that you would do in 1982. But for the problems of the size that you would use in industrial problems, or that you would use in the year 2000, or the year 2020, or the year 2050, well, those are the sizes where we have on the right-hand graph. And you see there that compared to the classical method, the more complicated method is essentially free. All right. So these complex algorithms mean the difference in taking time that's of the matter of seconds versus taking time that's universe lifetimes in duration. So theoretical algorithms are sort of in their golden years now, and this is one of the areas that computer algebra benefits from a lot. All right, so now how is computer algebra used? So we're saying we're doing this stuff. Is this just for fun, or are we just amusing ourselves? Well, this is actually used. Any work involving lengthy formulas uses computer algebra. So for example, in generating the Fortran programs to say where the moon was going to be. If you get in a rocket and you go up there, you hope the moon's there by the time you get there, right? So, all right, so you have to figure out where it's going to be, and that involves much more than just a simple elliptical orbit. It involves where's Mount Everest and Jupiter and all these things. And so the program to compute that was done with computer algebra, that generated Fortran program to compute the numbers. Martinez Veltman and his graduate student de Hooft, they got the Nobel Prize in 1999 for elucidating the nature of the electroweak interaction, so Yang-Mills theory. And Veltman built one of the first computer algebra systems, Schoonskip, in order to do the calculations for Yang-Mills theory. So this is a Nobel Prize as much for computer algebra as it is for electroweak interactions. All right, and there's also this cryptographic arms race, right? We'd like for our money to stay ours, and the thieves would like our money to be theirs. Okay, and computer algebra systems are using that all the time. Education has been the poster child of computer algebra. Using computer algebra systems in the classroom allows students to work with more interesting problems. And I have a few examples from engineering that I'm about to show where engineers have used computer algebra systems to make a faster design cycle, and they're able to try more things. So the first example here, these are 3 examples from MapleSoft, a company that has sprung up around the use of Maple. So modeling of the Canadarm and the Canadarm 2. It generates a mathematical model about how the Canadarm works using something called Symbolic. That model is taken and eaten by Maple and transformed, and C code is generated, and then the actual simulation code is spit out as C code coming from Maple. And this is particularly important because Canadarm is spindly. It has to operate in space. It doesn't have to operate in Earth's gravity. So we cannot actually operate the thing here on Earth. And so we have to simulate it. It's not a case of it being more economical to simulate. I suppose every time you want to do something, turn the knob an extra 25%, send up another rocket. I suppose you could say in principle you could do it experimentally, but in practice you have to do it with simulation. All right, another example is coming from computer animation. So another one of the groups using Maple is PDI DreamWorks. They use Maple for generating experimental shading models, volume rendering, for how to render smoke inside of an ant's cave, and all kinds of other important problems. Using partial differential equations to model how the rippling of the water goes in the movies, and so on. And lastly, here's an example of green engineering. This is coming out of a collaboration between MapleSoft and Toyota for high-fidelity battery models for hybrid electric vehicles. So this is a multi-domain model, meaning that they're considering things like the temperature and the chemistry and the physical mass of the battery. And this is all done using MapleSim. MapleSim's a program where you draw pictures, and behind the pictures, equations automatically get generated and then simplified, and then you're able to run your simulations. And by rearranging pictures on the screen, what you're doing is you're actually doing mathematics by changing the equations. Another example is this Sky Sails company in Germany that uses Maple to simulate its sail and control system, where basically the idea is pretend your cargo carrier is a kite surfer. And this is a way to reduce energy costs. All right, so I'll say a couple of sentences about my own research interest within this large domain. All right, so my interest in computer algebra is to expand the set of things that computer algebra systems can do, to expand the set of problems to which they can be applied. What new kinds of mathematics do we need to be able to do in order that they can be applied to a larger set of problems? All right, this involves working with compilers, developing new algorithms, human-computer interfaces, and the whole shebang. So one example here is something which I will call symbolic polynomials. And so here we see, this is really obscene, I know, for many people here, but just bear with me for a second, please. All right, so we see here these are polynomials. They've got x's in them, and the exponents have other symbols like m's and n's and so on. So normally we work with polynomials that are like x squared. Well, this is x to the sum formula. And if we know how to factorize and do GCDs and do all kinds of things with polynomials where they have exact numbers for the exponents, we might want to be able to do the same thing. We want to do the same thing for polynomials where we've got formulas in the exponents. Nobody was able to do that. So we had to invent some new mathematics, invent some new software, and now we can factorize such polynomials. Another example comes from some work with Professor Rob Corliss, an earlier distinguished university professor here at the university. We started working on this problem together in 1994 at the IBM T.J. Watson Research Center when he was visiting on sabbatical. So here I've got this polynomial x squared minus y squared. And many people here will remember that that can be factored into those two polynomials. It turns out that if we just nudge it a little bit, it can't be factored anymore. That's almost always true. You take something that factors, you take something that has an exact solution, and you nudge it a little tiny bit, it no longer has an exact solution. So the question is it near a problem with an exact solution? Because if it is, I could use that. All right? So how do you find a nearby polynomial that factors or does something else? So if we take that x squared minus y squared, y is x to the fourth, y squared minus x to the fourth plus a little tiny bit, it doesn't factor anymore. But if we nudge it a little tiny bit, we can factor into those things below, and that gives something which is only 10 to the minus, it's a small fraction of a percentage off from the correct answer. Mathematics on the internet is something I've been working on for many years, since the mid-90s. So MathML is now supported in many browsers. And so here's an example of a screenshot from Firefox running MathML. And lastly, for the last few years, I've been working on mathematical handwriting recognition. So the idea is to use a device that looks something like, that's a Victorian-era iPad up in the left-hand corner. And you can write on a pen with it. There's a setup in our lab with one of our former students. And the point is that we can take these symbols and we can map them into some abstract space, and we can ask whether the purple dot in the lower left is close to the red dots or the blue dots, each of those representing mathematical symbols. And so this is not actually in normal space. This is in where the x and y axis represent some weird things like how many loops they have and so on. But once you recognize the characters, that's not enough. You see in this middle example here, which I can't point to because this doesn't work, you see that this I under the sum of I, sum over I of I squared. Well, that's clearly an I in the first equation, but below it I've got z dot plus z equals sine omega t. And any electrical engineers in the room here will recognize that that first one has to be an I and the second one has to be a z dot, except that they're both pixel for pixel the same thing. All right, so there's no way to tell what they are, no matter how hard you look at it. And so that graph in the lower right hand indicates some of the statistical methods we use to differentiate from them. And this gets us into digital ink. So here's an example of some work done with my grad student Ray Hu is here in the room today. Here we're looking at a calligraphic drawing of the word forever. The middle stroke, this red stroke, we see in the second column the actual data that's measured for the x coordinate and the y coordinate and the pressure over time. And then we have this brush model for, depending on how hard you're pressing, and when you, so imagine if you're doing calligraphy, you've got a brush, you put it down, and you drag the brush has got a tail. Then you change direction. What happens? Well, we can describe this with math, as in the upper right-hand corner, but I was trying to get this across, and this is probably the most embarrassing, memorable slide I've ever given. This was, I had this presentation with that upper right-hand picture. And this was at the 90th birthday celebration for Wu Wensun, one of the most celebrated mathematicians in China. So as an invited speaker to his 90th birthday conference, I really did want to get the point across. And there, everybody's familiar with donkeys pulling carts. So what we see here is a donkey with a red rope attached to a wagon. This slide was actually in the talk, okay? And so this is showing how the brush model can be explained in terms of a donkey pulling a cart and the donkey changes direction, and that's somehow you relate that back to which way the bristles on the brush go when you change direction. And so they didn't remember any of the math, but they remembered the donkey. All right, so the big picture here is that we want computers to be as easy to use for math as word processors are for just typing in your letters and recipes and so on. And we're still pretty far from that. We like to be able to write our equations, to scribble them. We want to be able to collaborate over distance. So if you try describing equations over the telephone to your friends, they want to hang up on you. I don't know whether anybody in this audience has tried to do computer consulting for their aging relatives. and had that joyful experience of trying to explain something two-dimensional over the phone. It really brings all of your enzymes and all of your flight or fight hormones into play here. Okay, and so in order to get all this to work, you have to do new programming languages that are more capable of dealing with mathematics, new algorithms, new interfaces. So in many areas, to make computer algebra work and go beyond what we've been able to do with it so far, we have to extend many of these other peripheral areas, so dragging them also to deal with these new capabilities. So that's the picture. And I'd like to thank all of my students and colleagues, some of whom are here, most of whom aren't here, either from at Western or around the world. Thank you very much.